Imagine a tank rolling through a dense, snow-covered forest. It doesn't look like any machine you've seen before. It doesn't have a single, rigid hull plowing through the undergrowth. Instead, it moves with a strange, almost biological fluidity. As it approaches a steep, rocky ridge, the front half of the vehicle tilts upward, climbing the obstacle, while the rear half pushes from behind. It looks less like a piece of military hardware and more like a massive steel caterpillar. This was the UDES XX. It was an armored vehicle that bent in the middle. Designed in the secrecy of Cold War Sweden, the UDES XX was one of the most radical tank concepts ever built. It consisted of two separate hulls connected by a sophisticated hydraulic joint. It weighed 26 tons, carried a crew of 3, and was armed with a powerful 120mm cannon, the same caliber used by the mighty Leopard II and M1 Abrams. But unlike those conventional beasts, the UDES XX had 4 tracks instead of 2. The idea behind it seemed brilliant in its simplicity. If a vehicle could articulate, if it could bend and flex over the terrain, it should be able to go where traditional tanks would get stuck. It could snake through marshes, climb vertical steps, and traverse deep snow that would swallow a heavier machine. In the minds of its creators, this was the future of armored warfare in the difficult landscape of Scandinavia. But the experiment ended in failure, and the reason for that failure was so fundamental, so rooted in basic physics, that historians looking back decades later often wonder, how did some of the world's most talented engineers not see it coming? To understand why this machine was built and why it ultimately failed, we have to step back from the drawing board and look at the map. The UDES XX wasn't just a quirky invention. It was a direct response to a strategic nightmare. Sweden in the 1970s was a nation walking a tightrope. It was officially neutral, refusing to join NATO or the Warsaw Pact. But its military planners were under no illusions. They knew that if the Cold War turned hot, Sweden would be on the front line. A Soviet invasion across the Baltic Sea or through Finland was a constant, terrifying possibility. This strategic reality dictated everything about the Swedish military. Unlike the Americans or the British, who might have to fight in the deserts of the Middle East or the plains of Germany, the Swedish army knew exactly where it would fight, right at home. And home in Sweden is a landscape that is openly hostile to heavy armor. It is a land of dense, endless forests, where sight lines are measured in yards, not miles. It is a land of thousands of lakes and vast, soaking wetlands that can swallow a tank whole. It is a land of rocky outcroppings and deep winter snows. Defense planners knew they couldn't match the sheer numbers of the Soviet Union. If they tried to fight a conventional tank battle, lining up hull to hull, they would lose. So, they developed a doctrine based on mobility and ambush. They needed vehicles that could hide in the forests, strike quickly, and then vanish into terrain that the enemy couldn't follow. This philosophy led to some of the most unique armored vehicles in history. There was the Stridsvagn 103, the famous S-tank, which had no turret and aimed its gun by turning the entire hull. There was the IKV-91, a lightweight tank destroyer designed to float over soft ground. And there was the Bandwagen 206, a small, articulated transport vehicle that could go almost anywhere. It was this last vehicle, the humble Bandwagen, that would plant the seed for the UDES XX. In the early 1970s, the Swedish company Hägglunds introduced the BV-206. It was not a weapon of war in the traditional sense. It was a transport vehicle designed to carry troops and supplies through the roughest terrain imaginable. And it was a revelation. The BV-206 didn't look like a truck or a tank. It looked like 2 boxes connected by a flexible joint. The front unit held the driver and passengers. The rear unit carried cargo or more troops. But its true genius lay in its movement. Because it was articulated, The tracks on the front and rear units could move independently. They could contour to the ground, keeping maximum traction even on uneven surfaces. Furthermore, the vehicle was incredibly light. Its 4 wide tracks spread its weight over a huge surface area. The ground pressure, the amount of weight pressing down on every square inch of soil, was tiny. It was less than the pressure exerted by a human foot. This meant the BV-206 could drive over deep snow without sinking. It could cross marshes that would bog down a man walking. It could climb slopes that seemed impossible. It was, in many ways, a miracle vehicle. It was so successful that over 30 countries eventually bought it. You could find them patrolling the Arctic, climbing mountains in the Alps, and navigating swamps in the tropics. The success of the BV-206 changed the way Swedish engineers thought about mobility. They saw a vehicle that didn't fight the terrain, it flowed over it. And inevitably, someone in the defense establishment asked the dangerous question: if this works for a transport truck, why wouldn't it work for a tank? It was a logical leap. If you could build a tank with the mobility of a BV-206, you would have a weapon that could flank enemy forces through impassable terrain. You could attack from unexpected directions. You could retreat through swamps where the heavy Soviet T-72s couldn't follow. It was a seductive idea. But as the engineers would soon discover, scaling up a concept is never as simple as it seems. Physics, it turns out, does not scale linearly. At the headquarters of the Swedish defense establishment, a single, provocative question began to circulate. It was the kind of question that engineers both love and fear, because it challenges the fundamental assumptions of their work. If an articulated vehicle like the BV-206 could traverse terrain that stopped every other machine in its tracks, why not build a main battle tank using the same principle? This question emerged at a critical moment in Swedish military history. The Cold War was at its height, and the threat of a Soviet armored invasion across the Baltic or through Finland was a constant, terrifying reality. Sweden knew it couldn't match the sheer numbers of the Warsaw Pact. It couldn't build thousands of conventional tanks to fight a traditional war of attrition. It needed an asymmetric advantage. It needed a vehicle that could disappear into the Swedish landscape, the dense forests, the rocky hills, the deep snow, and strike from unexpected directions. To find this advantage, the Swedish military launched a massive research program known as UDES. The acronym stood for Underlagsgrupp Direkt Eld Stridsfordon, or Direct Fire Combat Vehicle Study Group. The goal was simple but ambitious: explore every possible design for the next generation of Swedish armor. Nothing was off the table. Engineers were encouraged to think radically. They studied turretless tanks, low-profile tank destroyers, unmanned turrets, and extremely light vehicles that could float over soft ground. The articulated tank concept was perhaps the most unusual idea to emerge from this program. It proposed taking the proven mobility of the BV-206 and scaling it up to carry a heavy gun and thick armor. If it worked, it would revolutionize armored warfare. A tank that could bend in the middle would be able to climb vertical obstacles, cross deep trenches, and navigate swamps that would swallow a conventional 60-ton main battle tank. Before committing millions of kroner to building a full-scale prototype, the engineers decided to test the concept with a smaller experimental vehicle. In 1976, they created a machine called the UDES XX. This vehicle was essentially a heavily modified BV-206. The engineers took the standard transport cabins and replaced them with simplified armored mock-ups. It looked like a small tank split in two. The front section housed a dummy driver's compartment, while the rear section carried a simulated engine and cargo space. The entire vehicle weighed only about 5 tons. Crucially, the UDES XX carried no real armor and no real weapon. Its purpose was purely scientific: to determine whether the principle of articulation could be applied to a combat vehicle, without sacrificing the legendary mobility of the BV 206, would have defeated a normal tracked vehicle. It crossed wide trenches by bridging the gap with its two hull sections. It drove over uneven, rocky ground where conventional suspensions would have struggled to maintain traction. The secret to its success was the articulation joint. This flexible connection allowed the front and rear sections to move independently, keeping all four tracks in contact with the ground at all times. When the front section climbed over a log or a rock, the rear section pushed it upward. When the front section descended into a ditch, the rear section acted as a counterweight, stabilizing the vehicle and preventing it from tipping forward. The engineers were impressed. The concept appeared to work perfectly. The UDES XX seemed to validate the idea that an articulated tank could offer superior mobility in the difficult Swedish terrain. But there was a catch. The prototype weighed only 5 tons. It was a light, nimble machine. A real tank would need to be much heavier. And as any engineer knows, weight changes everything. Encouraged by the success of the UDES XX, the Swedish procurement agency FMV made a bold decision. They approved the development of a full-scale combat vehicle based on the articulated concept. The new project was designated UDES 20. The number referred to its intended weight, approximately 20 tons. This was a significant leap. The new vehicle would not be a mock-up. It would be a fully functional tank, equipped with real armor protection, a powerful main gun, a 3-man crew, and a complete combat system. The design concept was ambitious. The tank would be divided into 2 sections, connected by a massive hydraulic joint. The front section would contain the crew compartment, driver, gunner, and commander, as well as the main gun turret. The rear section would house the engine, the transmission, the fuel tanks, and the ammunition storage. The logic behind this split layout was sound. By placing the engine and fuel in the rear, the designers could keep the front profile low and well protected. The crew would be isolated from the most volatile components of the vehicle, and the articulation joint would allow the tank to bend over obstacles, just like the BV 206 and the UDES XX had done. If successful, the UDES 20 would be able to travel through terrain that stopped traditional tanks dead in their tracks. It could flank enemy formations through supposedly impassable swamps. It could hide in dense forests where larger vehicles couldn't maneuver. It could strike from unexpected angles and then vanish into the wilderness. At least that was the theory. But as the engineers moved from the drawing board to the workshop, they were about to discover that the laws of physics are not easily bent. Designing a vehicle like the UDES 20 was not a task for the faint of heart. It required a level of engineering audacity that few nations possessed. The project was handed over to a joint team from 2 of Sweden's most respected defense contractors. Bofors, the legendary arms manufacturer responsible for some of the world's best cannons, and Hägglunds, the company that had built the miracle vehicle, the BV 206. The resulting design was a study in unconventional warfare. The UDES 20 was split into 2 distinct armored holes, connected by a massive articulated hydraulic joint. Each hole rode on its own pair of tracks. The power from the engine, located in the rear hole, was transmitted through a complex driveshaft system to the front tracks, allowing all 4 tracks to drive the vehicle forward simultaneously. The front hull was the nerve center. It housed the crew compartment, driver, gunner, and commander, sitting side by side in a low-profile armored capsule. Above them sat the main armament, a powerful 120mm smoothbore gun, the same caliber used on the mighty Leopard 2 and M1 Abrams. For a vehicle intended to weigh around 20 tons, this was an immense amount of firepower. However, fitting such a large gun onto a relatively small chassis created a unique problem. The ammunition for a 120mm cannon is heavy and bulky. There simply wasn't enough room in the front hull to store it safely. So the engineers came up with a radical solution. They put the ammo in the back. The shells were stored in an armored magazine in the rear hull, separated from the crew. But the gun was in the front. This meant the tank needed a way to move the shells from the back to the front, across the articulating joint and into the breech of the gun. The solution was a robotic arm mechanism. This complex system would reach into the rear magazine, grab a shell, rotate it, pass it through the joint, and load it into the gun, all while the tank was moving and the two hulls were flexing relative to each other. It was an engineering marvel on paper, but in practice it was a nightmare of complexity. In the prototype, the system was never fully installed. Instead, the gun was loaded manually during testing. As the engineers began to build the prototype, a familiar enemy emerged: weight. The original concept called for a vehicle weighing approximately 20 tons. This was light enough to be air transportable and agile in soft terrain. But as the design progressed, the weight began to creep upward. First, there was the armor. Both hulls needed to be protected against enemy fire, which meant double the surface area to armor compared to a conventional tank. Then there was the articulation system itself, heavy hydraulic rams and sturdy steel linkages. The complex transmission system to drive all 4 tracks added more mass. The massive 120mm gun and its turret added tons. And the engine, powerful enough to move this strange beast, was heavy too. By the time the prototype was finished, the weight had ballooned to approximately 26 tons. This was nearly 30% heavier than the original specification. At first glance, this might not seem catastrophic. After all, 26 tons is still light compared to a 60-ton main battle tank. But in the world of vehicle dynamics, weight is not just a number on a scale. It changes everything. The engineers had designed the UDES XX based on the assumption that it would behave like the lightweight BV206. They assumed that the wide tracks would spread the load evenly, allowing the vehicle to float over soft ground. But as the weight increased, the ground pressure increased with it. The square cube law is a fundamental principle of engineering. As an object gets larger, its volume, and thus its weight, increases much faster than its surface area. The contact patch of the tracks, the area touching the ground, did not grow as fast as the weight of the vehicle. This meant that the UDES XX was no longer a lightweight marvel floating over the snow. It was becoming a heavy machine, pressing down hard on the earth. The very advantage that had made the concept so attractive, its legendary mobility in swamps and snow, was slowly being eroded by the sheer mass of steel required to make it a fighting vehicle. The engineers had built a tank that could bend, but they had forgotten that bending doesn't make you lighter. And as they prepared for the first field tests, the physics of soft terrain were waiting to teach them a harsh lesson. The success of the BV206, the miracle vehicle that had inspired the entire UDES XX project, was built on a single crucial factor: extremely low ground pressure. Because it was so light and had such wide tracks, the BV206 exerted very little force on the ground. It could effectively float over snow, mud, and sand, distributing its weight like a snowshoe. But as the engineers scaled up the concept to a main battle tank, they ran into a hidden physics problem. The UDES XX was now more than 5 times heavier than the BV206 prototype. The weight had increased dramatically, but the contact area of the tracks had not increased proportionally. This meant that the ground pressure, the force per square inch pressing down into the soil, was significantly higher. The vehicle could no longer simply glide over soft terrain. Instead, it would dig in. The square cube law, a fundamental principle of engineering, dictates that as an object gets larger, its volume, and thus its weight, increases much faster than its surface area. The engineers had inadvertently designed a vehicle that was heavy enough to sink, but not heavy enough to crush its way through obstacles like a conventional 60-ton tank. The advantage of the articulated design was therefore reduced. The ability to bend over terrain was still there, but the ability to traverse soft ground without getting stuck was compromised. However, this problem would only become obvious once the vehicle left the drawing board and entered the real world. The first tests of the UDES XX prototype took place on solid ground. On roads and firm terrain, the vehicle performed reasonably well. The articulation system allowed it to climb steep slopes and cross wide trenches, just as the engineers had hoped. The 4 tracks maintained good traction, and the vehicle demonstrated impressive mobility over uneven, rocky ground. The engineers began to feel confident again. The concept appeared viable. Winter testing in snowy terrain also produced encouraging results. The vehicle performed roughly as well as Sweden's lightweight IKV-91 assault gun, which was considered a success. The articulation allowed the UDES XX to navigate deep snow better than many conventional tanks, thanks to its ability to push and pull itself out of drifts. But then came the real test. Swamps and wetlands were supposed to be the articulated tank's greatest advantage. This was exactly the terrain where the BV-206 had excelled, allowing Swedish forces to flank enemies through supposedly impassable areas. The UDES XX was designed specifically to dominate this environment. But when the UDES XX entered the soft marshland of the testing grounds, the results were disappointing. As the vehicle moved forward, the tracks began to sink into the mud. Slowly but steadily, the heavy machine became bogged down. The increased weight meant that the wide tracks could no longer distribute the load effectively. The ground simply couldn't support the pressure. In some cases, the vehicle performed worse than conventional tanks. A traditional tank, with its long, continuous tracks, creates a stable platform that can sometimes bridge soft spots. The UDES XX, with its shorter, articulated tracks, had less stability. The front section would sink, dragging the rear section down with it, or the rear section would dig in while trying to push the front section forward. The very environment that the design was meant to conquer had exposed its greatest weakness. The core assumption behind the project, that articulation equals superior mobility in all terrain, had been proven wrong. The engineers realized too late that scaling up a light transport vehicle into a heavy combat tank changes the fundamental physics of how it interacts with the ground. The swamp test was a turning point. It shattered the illusion that the UDES XX was a miracle weapon. But the problems didn't end there. As the testing moved to the firing range, another critical issue emerged, one that would prove even more fatal to the project's future. The UDES XX had failed the swamp test, but mobility wasn't the only concern. A tank is a weapons platform, and its primary job is to deliver accurate fire. This is where the second, and arguably more severe problem emerged. Because the vehicle was articulated, it consisted of 2 separate halves connected by a joint. As the tank moved over uneven terrain, the joint flexed. This meant the front hull, where the gun was mounted, was constantly moving relative to the rear hull. Every bump, every dip, every turn caused the front section to pitch and roll independently. This created large oscillations. The gun barrel would bob up and down with each articulation movement. In a conventional tank, the hull is a single, rigid platform. While it still moves, the suspension system absorbs much of the shock, allowing the gun stabilizer to keep the barrel level. But in the UDES XX, the entire front half of the vehicle was moving. The stabilizer had to work overtime to compensate for these large, unpredictable motions. Maintaining a stable aim while moving proved nearly impossible. The gunner would line up a shot, only for the front hull to pitch forward as the rear hull pushed it over a bump. The barrel would dip, then rise again as the suspension settled. This instability meant that firing accurately on the move, a critical requirement for modern tanks, was extremely difficult. The vehicle often had to come to a complete stop and wait for the oscillations to settle before firing. In the fast-paced environment of modern armored warfare, where seconds determine survival, this delay was unacceptable. A tank that has to stop to shoot is a sitting duck. Recognizing the severity of these problems, the engineers scrambled to find solutions. They proposed several improved variants, designated UDES 20B and UDES 20C. These designs explored radical changes. One idea was to move the gun further back on the front hull, to reduce the leverage effect of the articulation. Another was to lower the turret profile to minimize the center of gravity and improve stability. There were even discussions about modifying the crew placement to better isolate them from the motion. However, none of these proposed fixes addressed the fundamental issue. The articulation itself was the source of the instability. As long as the tank was split in two, the front hull would always move independently of the rear. And as long as the gun was mounted on the front hull, it would always be subject to those movements. The weight problem also remained unsolved. Adding more sophisticated stabilization systems or modifying the hull structure would likely increase the weight even further, exacerbating the ground pressure issues that had plagued the swamp tests. The project was trapped in a cycle where fixing one problem created another. Support for the UDES 20 within the Swedish defense establishment began to wane. The promise of a revolutionary tank that could go anywhere and do anything was fading fast. The reality of a complex, expensive, and flawed machine was becoming impossible to ignore. After months of rigorous testing and analysis, the Swedish Procurement Agency, FMV, reached a clear and damning conclusion. The articulated tank concept simply did not offer sufficient advantages to justify its cost and complexity. On firm terrain, the UDES 20 performed no better than conventional tanks like the Leopard 2 or the Stridsvagn 122. Its mobility was comparable, but its firepower and protection were arguably inferior due to the compromises required by the articulation. On soft terrain, the very environment it was designed to dominate, it was often worse. The high ground pressure caused it to sink in swamps where lighter vehicles like the BV 206 floated effortlessly. The articulation, which was supposed to be its greatest strength, turned out to be a liability in deep mud. Furthermore, the vehicle was mechanically complex. The hydraulic joint, the dual drivetrains, the robotic autoloader, all of these systems required specialized maintenance and were prone to failure in the field. The cost of building and maintaining a fleet of UDES 20s would have been exorbitant compared to buying proven, off-the-shelf tanks. The decision was made. The UDES 20 project was canceled. Only a single prototype had been built. The dream of the articulated tank was over. The surviving prototype of the UDES 20 was eventually placed in the Arsenalen Tank Museum in Sweden. Today, it stands as one of the most unusual armored vehicles ever created, a testament to a time when engineers dared to challenge the fundamental rules of tank design. Visitors who encounter it are often struck by its strange appearance. The two hulls connected by a massive joint, the 4 tracks, the robotic arm for the gun. It looks like something from a science fiction movie, a vision of a future that never quite arrived. Although the UDES 20 failed as a combat vehicle, the research conducted during the UDES program was not wasted. The engineers gained valuable experience in vehicle layout, crew ergonomics, and experimental turret systems. The articulation concept, while flawed for a heavy tank, proved its worth in lighter vehicles like the BV 206 and the BVS 10, which remain in service around the world today. Some of the ideas explored during the UDES program later influenced successful Swedish designs. The focus on mobility and low ground pressure informed the development of the CV-90 infantry fighting vehicle, one of the most capable armored vehicles in modern service. The lessons learned about gun stabilization and fire control contributed to the advanced systems found on the Stridsvagn 122. The project also provided an important lesson for military engineers everywhere. In the pursuit of innovation, radical ideas can sometimes lead to breakthroughs, but they can also lead to dead ends. The UDES 20 remains a fascinating example of how an idea that seems brilliant in theory can collapse when confronted with the harsh realities of physics. There is something deeply compelling about a machine that refuses to conform. In a world of standardized main battle tanks, where the Leopard 2, the M1 Abrams, and the T-72 all look remarkably similar, the UDES 20 stands out as a bold experiment. It represents a willingness to question assumptions, to rethink problems from first principles, and to take risks in the name of progress. The story of the UDES 20 is not just a story of failure. It is a story of ambition. It reminds us that progress often requires failure. Without the UDES 20, we might not have learned the limits of articulation in heavy armor. Without the failures of the past, we cannot build the successes of the future. Thank you for spending part of your day with us to explore this unique chapter of military history. If this story of engineering courage and the pursuit of the impossible resonated with you, we'd be honored to have you with us again.